then the system may lose energy by also either of those two options. And of course, that's what we are after. As I mentioned, I want to hopefully get you to the point before this 4 chapters are done to see how we can add heat energy to a system, and what comes out of the system is then work energy. And so we can convert heat into some kind of work. So that's kind of the ultimate goal. I showed you the one that bursted into flames, and probably will show it again here by saying I can do work, and then the work can turn to heat, and of course that ignited the paper on fire. And so there's a lot of different things that can happen, but the short answer here is that it's all conservation of energy. One thing I didn't show you is I said, you know what we could do is we could integrate both sides of this equation. And when we integrate it, what we come up with is, okay, this is the total Q and this is the total W. And so as we squish it down, we can be saying, look, how much is done? On the other side, we can write this as E. Here's something that I think is a little confusing, but nonetheless, it's the notation we use, so let me point it out. We call that a delta E. In other words, this is the net energy gained by the system. And actually, that probably makes more sense, but I would also say this is a delta, right? And this is a delta. But that's what we always mean by heat, right? Heat was defined a chapter ago as the amount of energy that transfers. I mean, so there's no point in putting a delta in front of it. So I don't know how you want to think about it, but basically these are all changes. Whether you write it with a delta there or not, like I said, it can get a little bit confusing, but this is the net change. This is how much went in minus how much goes out. This is the change in energy. This is the change in energy. The two added together are the change in energy. Now, before we even got to this, we said here is a couple of ways of calculating thermal energy. You could do it by either the specific heat or the latent heat of fusion or the number of moles, and we could use the molar specific heat, either a CP or a CV. So again, we got to have more of a discussion on that one. Also, the amount of work, we have to have a discussion. But let's just make sure I got this picture, because here is I think the hardest part of doing the calculations for this chapter and next and beyond is, let's look at something like this again. Let's put a couple of weights. Let's warm it up to 80 degrees Celsius. So, got the hot water, I can warm it up. But to warm it up to 80 degrees could be done in different ways. If I close the clamp back here, so the piston can't go up, and I put it in the hot water, that will warm it to 80 degrees. Fair enough? And that means right now, Q, thermal energy, is going from the hot water into the gas. But there's other ways to warm it to 80 degrees. Let me cool it down first. I'll put it in some ice water. And make sure this picture is clear in your mind. I don't know if that was... Oh, that's a little cold. See where I am? Oh, yeah, it went down a little bit. Okay. Maybe I'll just add a little air to start it off the bottom there. Okay. But with the clamp loose and warming it to 80, still warms to 80. Did it take the same amount of energy to warm? No. Are you seeing that? Why not? Why would it be different, and which one would have more?
The second one, because you put work that went out of the system.
Right. And this is that silly example I said of, think of this as a 5-gallon bucket with a hole in it. See, if no energy was coming out, if the clamp was closed and the piston can't go up, the piston can't do any work. And therefore, all the heat that I add to it is only going into making the molecules go faster. And it gets up to 80 degrees at a lower amount of energy than if I was having the weights rise. And if those weights go up, then here's what happens. As I'm adding energy and trying to warm this up, in the process of warming this up, some energy is coming out, lifting the weights. So ultimately, I have to put more energy in to warm it to 80 degrees because I'm losing some energy. Make sense? And you got to have that conceptual picture. I say that because, again, the most important thing I can say here is, and your author puts it this way, is this number. Calculating how much heat or calculating how much work are what we would call in a math class path dependent. And what we mean by that is calculating them really depend on what happened. Did you lift a weight or was it clamped? Did you do this or did you do that? And so we're going to spend the balance of the rest of this chapter and next chapter and the ones beyond calculating these, but we have to stop and ask ourselves what's going on. I wish it wasn't, because here's what's going to happen. When we have a list of how to calculate heat, this thing is going to be enormously long. Too long that you don't want to memorize it. You want to have to derive it each time based on what is going on for that particular problem. That's really the key here. Okay, question?
So just in a combustion engine, just by moving the piston itself, it's cooling itself down?
Yes. So when the piston expands like this, and the whole reason you're having the piston in an internal combustion engine expand is you're trying to push the car. You're trying to make some of the heat energy go into pushing the car. So when a car is going down the road at 50 miles an hour and you ask yourself, where did it get the kinetic energy from that? The answer is from the heat of the burnt gasoline. And so as it expands, the gasoline is cooling. Yeah.
So that's why when you're going up a hill, the engine tends to overheat because there's more pushback on the piston?
In part, yeah. Okay. Yeah. Yeah, I mean, you're just asking more work from it, so it's burning more gasoline. The more gasoline, a percentage of that goes into heat, and you got
If you had an engine in neutral and you just revved it, there's no resistance, there's no pushback.
Right, right.
So the piston would be free to expand.
Right, and then the computer would give it very little gasoline. And the computer said, okay, don't burn much gasoline. And if you don't burn much gasoline, then very little is heat to begin with, and then very little goes into the heat of the engine, and the engine doesn't overheat. Also, when you're revving it, I mean, that gets more complicated because revving it then also circulates the water real quick. So a car in neutral can cool pretty quickly because you're pumping the water very quickly and you don't have a load on it. Yeah, you start going up the hill and you bog down. You don't have the high RPMs, so you're not circulating the water as well as you're asking a lot of work from it. Yeah. Well, as I was getting to, and I was going to wait a minute, but since you're asking it here, it's probably worth seeing. Remember this one? Let's do it in more slow motion, if you will. Look at this one here. This is kind of a bigger version of this one. Okay, this one, I pushed the piston down and I did work on a small amount of gas. This one is built and designed, as you can kind of see, with a temperature gauge in it, so that you can actually see it. Here is a 2-liter bottle. Here is my piston. And so if you imagine the air in here, as I slam it down, it's going to get put into here. I am going to do work on it, and its temperature should go up. Now, not as much as it went up here, so nothing inside is going to catch on fire, but the temperature gauge will go up. But I thought it would be worth today to take a moment to get this mental picture. Look at this one here for a moment. Looking at this baseball player, hoping to hit a home run. How? What do you need to do to hit the home run? Does that ball go fast or slow? Fast. How are you going to make that ball go fast? Yeah, you come in, and if you look at the player, he's going to plant his back foot, he's going to push with all his might, ball comes in, and it's a hard push, right? You're shoving that ball as hard as you can. And a result of that is that ball ricochets off the bat really fast. Same mental picture. What would happen right here? I have a piston, I have a bunch of molecules. As this piston comes slamming down, Isn't that like the baseball bat? Hitting a bunch of molecules? I mean, what's going to happen when this piston comes in and hits all those molecules? And makes them go faster. And what is fast molecules? Heat. And so again, shouldn't be too much of a surprise whether we look at it in terms of, hey, you're doing work on the system that can convert it into heat, or looking at the molecular picture that what's going to happen here is if this baseball is representing some nitrogen molecule, when you come in and you hit that nitrogen molecule, it's going to go faster now. And that faster is a higher temperature. And so, if everything is set here, I will push on them. Anything change? For those of you who are closer, can you read it? It's 23 now. Why don't I do it a second time? What's it now? 23.7? How about again? How about again? How about again? Again, 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 again. Now, there's a lot of air in here. I hope it's going up. Oh, good, 33. And again, and again, and again, and again, and again. All right. And so let me get to about 40 psi. We there yet? A little more? All right. But it did get pretty warm. Maybe a couple more. Oh yeah, I can feel warm. Yeah, all right. But it's 36, and it's probably getting so hot now that what else is happening? Yeah, now, as the system has gotten hot because the work has been done on it, or to put a better visual mind here, is my piston has come down and hit the baseball and made those baseballs go faster, then I have the system that is hot. And of course, something in a hot room, what's going to happen? It's going to lose, right? And so right now, it is cooling down. And so we are losing thermal energy to this room. And so now it's down to 28. And I can leave it here for a while. I just hope I'm not losing pressure. Good. Because if I wait a while, the temperature will come down to room temperature. Because let's see the opposite of this. So far, I have shown you me doing work on the system, converting into heat. What if the system did work? What if the system was expanding? What does that mean? It's coming from the gas. And where does that energy come from? The gas, right? Let me change the picture here. If this helps, how do you bunt a baseball? How do you take a fast pitch and slow it down? Yeah, here comes the baseball. And if you hit something solid, it would just bounce off and go straight back, right? And of course, if the bat's swinging into it, it goes off faster. But what if the bat is soft? Well, not the bat itself, but the person holding the bat softly. What happens if the ball hits the bat and the bat goes backwards? What happens to the ball? Yeah, it either stops or bounces forward very slowly. Fair enough? But the point is, if what you're hitting is moving backwards, the ricochet off can be at a slower speed than what came in. And if these are molecules, in other words, if I take a gas and it expands, the container itself, and in this case I'll just draw a picture and say, look, the container is the air around it. But if I have a gas right here, which in this case I have gas right here, and if I open that valve, as that valve opens up, it's going to expand. And as it expands, it's bouncing off these air molecules that are moving backwards. What's going to happen to those molecules as they bounce off? Yeah, they're going to go slower. It's going to be like a bunt. And so as this gas expands, the molecule will hit it and bounce back slowly. And so the gas is going to cool, right? The molecules are going to be going slower. In this sense, in terms of energy, I'm doing work. And as the gas expands and does work on the environment, because remember, this is the air pressure. You got to push the air molecules back. And so as the gas expands, it's doing work. Where does the energy come from? The motion of the molecules. The motion of the molecules, it's its temperature. And so this temperature is going to go down. And yes, this is how you make a refrigerator. This is exactly the whole idea. A combination of a compressor and an, well, evaporator, but I'll call it an expander for now, okay? And you gotta let it expand. So I waited long enough purposely to see the temperature. It's cooled down to about room temperature now, 21. But it's still under a lot of pressure. So if I pull the pin on here, I'm hoping it will expand. And in the process of expanding, keep an eye on the temperature. 21.4. And cloud, and oops, thermometer fell out. So cold, but cloud gone. And so it got so cold that the moisture that was in there condensed. And bummer, the thermometer blew out on that one, huh? Got to do something better with that. That happens a lot. But usually goes down to about 4 or 5 Celsius in there. It can be cold, yeah.
So when you're like filling up your tires, should you wait after you put the initial air in and let it cool down a little bit?
Sure. Now you're down to an issue of how exact does it have to be, But when you look at your car pressure, if you open up your car tire, it'll say on the side, fill it up. On mine, it says 35 psi, cold psi. And it's very particular about cold, because if I were to fill it up a lot, now if it was already, say, 33 psi, and I put 2 more in, it has warmed it a little bit, but it's pretty close. So I've got no problem adding 2 pounds, and not waiting. But if this was a completely flat tire and you were completely filling it up, yeah, you better, you're not going to get a right reading. You fill it up to 35 psi, but it's hot 35 psi. And then, of course, it's going to cool down. Yeah. But I don't know about any hotter than if you were just to drive your car and then test it. I mean, that's the other thing, too. People will test it after they've driven it. That's not a good time to test it. It's before you drive it. Then you see what the pressure is.
So wait, wouldn't it theoretically that you can do 2 different kind of gases, like a pre-compressed tank of gas and a compressor kind of thing? So the pre-compressed gas is already at room temperature, but it's under pressure. So when you let the air out, it gets really cold, and the compressor machine, when you put gas into it, it'll make the gas come out very hot because it's compressed and it's cool.
No, it is. I would say that's not 2 different kinds. That's the same thing. If I run a compressor, I turn on my compressor in my garage and it pulls the air in, it's compressing that. And if I put my hands on the tank, it is warm. It is very warm.
And a tank of pre-compressed gas is room temperature already, but under pressure. So
Only because it cooled down.
yeah.
Okay. So then, like this one, once I take my compressor and I start blowing the dust off of my workbench, as that gas expands, it is going to cool. And so if it was already at room temperature in my garage, then the tank's going to be very cold.
That's why you're saying we need to just derive these equations every time.
And that's why I'm saying, exactly. The situation is different every time, and it's not so easy to say, do this. I wish it was. That's why we use this word path dependent, meaning how much energy goes into work, how much goes into thermal, all depends on how you heated it or how you cooled it. And that's what makes this challenging. Okay, now let me compare that to what we did with a roller coaster in mechanics. If this was a roller coaster up here, and I say, okay, here's my roller coaster at the top of the hill, and it goes down to this height, could you calculate the speed at that height? Well, didn't we use potential energy and say, well, sure, mgh equals 1/2 mv squared. But what if the roller coaster, I'll change colors here, did this? What if the roller coaster went down and back up? What's the speed when it gets here? It's still the same. You see, all we cared about when we had EV equations, when we had what we are going to call state functions is we only needed to know the change in height. And it didn't matter which path that roller coaster went in if we ignored friction. If we included friction, then it mattered. And so then we had a path-dependent problem. And it was a much harder problem, right? But if that roller coaster were to get to that same height, regardless of what path it takes, we only cared about the change in height. And that is called state functions. And so this book and me are going to make a big deal out of it. What do we do when we have a path-dependent path? And what do we do when we have a path-independent path? Path-independent ones, which we call state functions, are wonderful. All you need to do is to tell me what's the change in height. You don't have to tell me how it got to that change of height. Does that make sense? But, as you're seeing, does the work or the heat act like a state function? No. It acts like a path dependent. There is some good news here, though.
I don't know if this works, but the fact you're saying it's like path independent, so it's like the idea with line integrals. Would you use them to calculate?
Oh, yeah. So you might even call this a line integral in the sense that how we get to the total work depends on what path, depends on what line it takes on a graph. Yes, that would be a good terminology to tie it into your math class. We won't use that terminology because you do line integrals in, which one? 200. In 200. And as you know, this class is all designed to use up to Math 160. But essentially we are doing the same thing, just not calling it a line integral. And in fact, I'll show you what a line integral is in just a second, but I want to emphasize this. Here's kind of the neat thing about it. Take advantage of this. How about the total energy? Isn't the total energy the molecular motion of these molecules bouncing around? Isn't it the kinetic energy? And what we just said is, isn't kinetic energy a state function? You don't care how it got to that speed. Did it get that much energy because work was done on it, or did it get to that much because heat was added to it? It doesn't matter. It could be 50% heat and 50% work, or it could be 25% heat and 75% work. It doesn't matter. If it gets to that temperature, we know the total energy it gained. Fair enough? So, as much as I made a big deal, and I want to keep emphasizing that these matter what path they take, this one doesn't. And so what's very helpful is calculating one of these might often be a little easier not to actually calculate Q, but to calculate the E and calculate the W to get the Q. And so, one of the most powerful equations I can put under here is to say the change in energy minus the work, because this has only to do with its temperature. Now, granted, this is path dependent, but here's my hint for you as you try to do some of these homework problems. This may be hard to do, maybe impossible to do. And this is just reasonably hard to do, and this is simple. And if we do these two, we can find that. Or over here, how else could I get work? I could get that. So put that in your library of tools here, because there's going to be many times where you'll be asked, calculate how much work, and you'll go, ooh. Or calculate how much heat, ooh. But you'll be able to get the other one. So there's only one really that we need to do of the hard ones. And so pick whichever one is easiest. This one is often easy. All you got to do is temperature change. More on that in a minute here, but it's a state function. So keep that in mind. We don't need to know how it got there. We just know it's beginning temperature and ending temperature. Yeah.
So when you took this example here, you're losing temperature while you're putting energy into it.
Okay.
You would have no way to know what delta E was.
Well, okay, so the one I just opened up and expanded, right, which we're going to call adiabatic here in a second. We're going to call this an adiabatic expansion. I would say I did it really, really quick. Okay? And the first thing I would say is I know that one. It happened so quickly there wasn't time for it to add energy or cool down from the room. And so that one's 0. If I want to know how much work it did, that might be a hard integral to do. But if my temperature probe stayed in there, I would have its initial and final temperature. And so I could calculate this easy. I know that's 0, and I can get that without really doing the work calculation. I would do the heat and the energy calculation. That's what I'm getting at. And will be in just a second. Well, the diagram I had on the board was, as you called it, a line integral here. Maybe I don't need to say it a fourth time here, but it, again, just probably needs, yeah, but I'm going to say it a fourth time whether I need it or not, is your author gives some good pictures. What did he do with what happened to that picture I had? Ah, right here. By saying, look, if this is a gas, okay, and let's say the gas starts right here on a diagram, all right, well, I'll start there. This is a graph. This is what we are going to call a PV diagram. And so, one of the ways to analyze our thermodynamics and what is happening is to look at what we call a PV diagram. I would classify a PV diagram as valuable in thermodynamics as those free body diagrams were in mechanics. The mechanics idea was kind of just separate everything else and look at just the forces. And that's what we have here. In this graph, I have a P and a V. And so we call these our PV diagrams. What are they really explaining? Well, look at this. What is this saying? Work is what? Work is the integral of pressure and volume. And so if you have a plot, let's say this one here, and you say, I have a gas starting right here. That's what the I for is, initial. And so it's got initial volume and initial pressure. So you might say it has a large volume and a low pressure. And then somehow it gets to here. Now they show a path. But the whole point of the three of these is, again, it starts here, finishes there. Starts here, finishes there. Don't they all start at the same place? Don't they all finish at the same place? But is the amount of work the same? The question is, how much work? Well, again, let's look at a PV diagram. What is this equation telling you? Isn't that the area under the curve? Isn't this the vertical axis? Isn't this the horizontal axis? And so you're saying the work is the area under the curve. If we go back to mechanics, if I made a plot of force and distance, and it looked like this, didn't we say the work was the area under the curve? And so we're doing the same thing here. We are going to say that if you start here and you finish here, the work is the area under the curve. So the question is, how did it get there? And so hopefully you can see that these are three examples that it got there differently. This one went from an initial volume to a final volume with essentially the same pressure. Once it got there, then, without changing the volume, the pressure increased. If I was actually trying to do this experiment, let's see, I guess I would start something like this. Oops, let me cool it down. So let's say I was at room temperature. What this is saying is I have a fairly low pressure, so I won't put any weights on here. I will give it, looks like a lot of volume, so I'll lift it up to here. And there's my starting condition. And so this first part is saying do what? Lower the volume. But lower the volume by keeping the pressure the same. Oh, how am I going to do that? Well, isn't the pressure determined by...
You let the air out.
No, I don't want to change the number of molecules. So what are they really saying as I go from here to here? How do I lower the volume and keep the pressure the same? Yeah, I'll cool it down. There we go. So that's the first part right there. And it gets lower and lower and lower, maybe right about there. I'll stop it. So I'll tighten it up. So I have just went from a lower volume, keeping the pressure constant. Now what's the next step? Get to a higher pressure without changing the volume. Well, that's why I clamped it. How am I going to get to a higher pressure? Put it in the hot water. So there's the second part. And so as I put it in the hot water, it's going up to there. Okay? And so this part, I have compressed the gas at a constant pressure. We're going to use a fancy name, isobaric. This is the isobaric process, same pressure. The word baric comes from the whole idea, you might actually, your book doesn't even use it, but another unit for pressure is a bar. So isobaric. More on that in just a second. But I just wanted to show you, what about this one? Well, there I've changed the pressure without changing the volume. Isovolumetric will be our fancy word there.
What is the prefix ISO?
ISO's what? No, don't change? Same? Yeah. Yeah. Well, and I'll put these on the board here in just a second, but what I wanted you to see here is compare that to this. This is a different process. Is the work done here the same as the work done here? No. Remember, the work is the area under the curve. And so the reason your author has this, and the reason I'm putting it up here, is because one process could be this, and this would be the amount of work. But another process could be this, and so the amount of work is much bigger. And a third process could be this, which the amount of work would be there. And I think you're seeing my point here, is that I gotta pay close attention to how do I get to the final state. To figure out how much work is done, watch the process of getting there. So, let's look at all these. I gave you 2 of the 4 names we're gonna study. Let me start with what I would call the easiest one. It's the one that would be going from here to here. It would also be here to here. But if you don't change the volume, what happens? So I will put this in as category number 1. What if the volume is held constant? Isovolumetric. Right? Don't change the volume. Let's look at this for a second. Probably the easiest one to ask here is how much work is done during an isovolumetric process. It's 0, right? You can't do any work because work is force times distance. We haven't changed the volume. Or put another way, look at this graph. How much area is under a straight line? On a PV diagram, we're looking at this. Here's P, here's V, here's the initial, here's the final. If you go from here to there, or if you go from there down to there, I guess it doesn't matter which way I go. Obviously, to get more pressure, I got to warm it up, and to get less pressure, I got to cool it down. But if I leave this clamped, the isobaric process, no work is being done. All right. What that tells me from my thermodynamics then is the change in internal energy would be equal to the Q. These are the simple ones. These are the ones that you've been doing. These are the ones that you did back in Physics 102, right? This is an isovolumetric process. You said, how much heat does it take to warm up a piece of lead 3 degrees? You just calculated the heat energy. You didn't do any work on the lead, and the lead didn't do any work in the environment. I guess there's a little thermal expansion, but forgetting the thermal expansion, we can say that the piece of lead, when you heat it or cool it, doesn't change its size. And so again, the easiest one, and like I said, maybe the less interesting one, is right here, the isovolumetric. Now, with that said, what else could happen? Well, they could change a lot differently. The second one I mentioned, and a pretty easy one to do experimentally, is what if the pressure doesn't change? And as I said, that one's pretty easy, because that would be something just like this. Loosen the clamp, and the pressure is determined by a combination of the atmosphere and how much weight you have. So as long as I leave the weight on here the same and the atmosphere keeps the same pressure, I can cool this down, or I can warm it up. But that process has the same pressure. So what would that look like? Step 2, if pressure is equal to a constant.
And that was isobaric.
Yeah, isobaric. And so there's my isobaric process. What would it look mathematically? Or what would it look like on a PV diagram? Well, that was really this first one I was showing you. And this one I didn't actually show you, but it's across the top, right? Isn't that the same pressure? Isn't that what that means on a graph? So isobaric means go from here to here. And so we can go from initial to final. Or the other way around would also be isobaric, whether we're going to bigger volumes or smaller volumes. So heating it up goes to bigger volumes, cooling it down goes to smaller volumes. But I'm hoping you see the conceptual picture before we get too lost in the math here. As I cool it down, does it take the same amount of energy to cool it down? Let me just do it again, like this. Let me warm it up first. So let's say we start with it in this position where it's warm. It's warm, and it's at a big volume. So I start here, okay? In order to cool it down, heat has to come out of here, right? Q. And in the process of cooling down, energy's coming out. Of course, the piston went down. Would that take the same energy out as if I did it a little different? Let me warm it up again. What if I let it warm up till it gets to the top here, okay, and let me clamp it again. And let me cool it down. And so now I'm cooling it without changing the volume. Does the same amount of heat come out of here? No. The amount of heat depends on the process I did. Which would have more heat coming out, and which would melt more of my ice in here? This one or the first one? Wouldn't the first one have to take more heat to come out of it? Why? What about the work? Right. This one, where the volume is held constant, all I've got to do is take it at a temperature of 80 degrees and slow down the molecules until they're 0 degrees Celsius. But if I start with them at 80 degrees and this clamp is loose, as I go to transfer them over to here, and the heat starts to come out, slowing these molecules, what does this do? This is doing work. This is adding energy back to it, tending to warm this up, which then has to come out to melt my ice. And so more energy has to come out during this isobaric process than the isovolumetric process. Wow. And if you got that, you're good for the chapter. I mean, that is really the point. The point here is the process matters. They're not the same. And we got to look at the conservation of energy. It's not just the heat coming out making the molecules go slow, but it's also, is energy coming in or out by work at the same time? And when you see that, then the problems kind of fall in line there. And so, as I said, more heat is going to come out as I cool this down than when I cooled it down here. The actual process is different. And you can see that in the math, I hope. Let's do this. One of the easiest calculations for the isobaric anyways is right here. I guess I should have put 0 here for the work. I guess that was a pretty easy calculation too. I mean, how much work is done for the isovolumetric? 0. There was no change in volume. This one, there is a change in volume, so there is some work, but fortunately it's not a hard integral to do. What's this one become? So, I can pull the pressure out in front of the integral. Why? Yeah, because it's a constant. And so this is why I showed these two first. Those are easy integrals to do. This one is just, hey, 0. This one is P dV. In fact, it comes out to be this then. Minus P final volume minus initial volume. And so there's the work being done during the isobaric process. And again, I would encourage you to remember this and work this out. Remember this and work it out. There's going to be many different processes of, okay, what happens during that process. And in fact, if I continue with my math here, the first law of thermodynamics then, which says this, would mean that if I was going to calculate Q, and then back here I would just need to know the change in temperature. Here, to calculate the Q, is a bit more. I have to take the energy, the temperature change, and subtract the work. And so the Q becomes delta E, and when I put this into here, the two negatives cancel, and I get P final minus initial. And maybe I'll put a little box around it. I don't know if that's good or not. I put a box around it. You might want to try and memorize it. But again, I don't think that's a good idea. It's not memorizing the equation for this case. It is understanding how you are going to get the equation for this case. It's path dependent. And now you can see what I was saying earlier. Which one had more heat coming out of it as I cooled it down? Can you see how this calculation is going to come out bigger than this calculation? If you cool down the molecules from 80 degrees to 0 degrees, this is the same. That's what I was saying, what's neat about a state function. With a state function, you don't care how it got to 80. Did it warm up past 80 and cool down? Did it just go straight up to 80? Who knows? But it has a certain energy at 80 and it has a certain energy at 0. And so whether the process is isovolumetric or whether the process is constant pressure, I can say that the heat is different because the change of internal energy of my gas is the same. But the reason I had to take more energy out of the isobaric process is because as I was cooling it down, more energy was going into it because that piston was coming down and doing work on it and making those nitrogen molecules move faster. And so as you correctly said, yes, when you put it in here with the piston going down, you are going to melt more ice. If the piston didn't go down, you would melt less ice. And so calculating how much ice melts is dependent on this versus this. How did you cool it down? Did you do it with constant volume or did you do it with constant pressure? And it all comes back to the fact that you are adding energy. And they get better. What about constant temperature? What if the temperature was held constant? Ah, good. You're seeing ahead here, right? There are times where we'll say the constant will be held. The temperature, will be held constant. And so we will call this the isothermal process. And again, looking at our equation for work, or helping us understand our equations, let's look at a diagram. Let's look at that PV diagram. As I said, PV diagram, a really useful tool here. But on this PV diagram, what would it look like? Well, I haven't written it down already. I probably should have. But don't forget from the last chapter, the ideal gas law. PV equals nRT. And PV equals nRT is true here and true here and true here. It's true for any of these processes, right? We said it's just that's true for all the gases. I didn't really discuss it on here, but here it becomes worth discussing here, because what you're really saying then is P times V equals a constant. And so looking at a PV diagram, they would not be nice straight lines. This is a vertical line. This is a horizontal line. What would I have here? Yeah, and so something that started here and moved to here, or started here and moved down to there. I think in this diagram they have us going from low pressure, high volume to small volume and high pressure. But whether you move one way or another, you are going to be following the shape of a hyperbola. This is the x times y equals a constant, and it might have been a while since you've done algebra 2, right? That's the equation for a hyperbola. And so it has a shape to it. We won't really worry about the mathematical name of it. Why don't we call this an isotherm? And so we'll call it an isotherm. And so that's what it would look on the PV diagram. And of course, the work would be the area under the curve. And again, hopefully it's becoming quite clear that the work is different in all three cases, right? You don't get the same work. It doesn't require the same heat. The process needs to be examined before you can say how much work or how much heat. What process did you do? Isovolumetric, isobaric, or in this case, isothermic. And so, do I have enough room here? Can I do this integral? And again, it's a little bit harder, right? Easy, somewhat easy. Medium? Oh, good. So you guys see it. It is a natural log. I could put in, and using this, I can write it as nRT over V dV. And that's the important step, right? The pressure does change. So, unlike this one where the volume didn't change and I just got a 0, that was easy. Unlike this one where the pressure was constant, I can pull it out. Here the pressure does change, and I need to know how the pressure changes in order to do the integral. And that's where the ideal gas law comes in very useful. And more than that, this is an isotherm, so what do we say about the temperature? It's constant, so I can pull it out in front of the integral. And now I have a reasonably simple integral to do, but I think getting there was important to see, plugging in the PV equals nRT. And now, what is the integral of dV over V? Yeah, it's the natural log of the volume evaluated from initial to final. So this becomes a minus nRT natural log of final over initial. And so there's the work done in the case of an isotherm. And I've kind of run out of room, so I'll continue on over on this side of the board. But just like in all these cases, we did the calculation for the work, we looked at a PV diagram, and then we did the first law of thermodynamics. We can really do the same thing again. We could say delta E is equal to Q plus W, right? And I just did the W. I just did the work. The work is a negative nRT natural log of final over initial. Oh, by the way, maybe I should point out, your author doesn't put a negative here. That could throw you for a loop. Why not? Because then you can flip the natural log. And so don't forget your properties of logarithm. This is the same as nRT natural log of initial volume over final volume. And so he prefers without the negative sign. I'm not real sure why, because I always like to think of it as final and initial, comparing final to initial. Got no problem with the negative sign there. Plus, I'm going to move it to the other side of the equation here in just a second. So I kind of like the negative sign, because here's the other part of this. What's this? Did you see the 0? Why 0? Right, and again, that is the state function one. That is the one that I'm trying to say. That number, that internal energy, is related to the kinetic motion of those molecules. And the temperature is related to that motion. And this whole process was called an isotherm, meaning don't change temperature. So we are not making the molecules go any faster or any slower. If I tried to show an isotherm process, it might look something like, well, this. It's already cold. I'll leave it in there. If I take some gas and I put it right there, this gas is at 0 degrees, or at least that part of it is. This part is kind of out, so it's not like the whole gas is the same temperature. But it makes a good illustration here is right now I have a 0 degrees. If I were to follow, say, this path, what this path is saying is make the volume smaller and the pressure go up. How can I do an isothermic process? Well, I guess I could start piling more weights on here. Right? That's more pressure. It's also less volume. But if I do it kind of slowly here, as this goes down and does work and tries to warm up the gas, what happens? The bath here cools it down. And so this, if done slowly, is what I would call an isotherm process. It sits in the bath, and every time I try to squeeze it to warm it up, it tries to warm up, but my ice water keeps it cool at 0 degrees. And so something sitting in a bath would be a good example of an isotherm. So again, as we do the problems, we got to stop. We got to think about it. What process is this? Is it constant temperature? Is it constant volume? Is it constant pressure? Because each of these have an important difference in my logic. And so the Q becomes nRT ln of final volume over initial volume. And this is a really good example of what I would say if you had an isotherm process like this. And just going back to where we started with the object up here, if I have it up here and I go to add pressure on it, and as I add pressure on it, some thermal energy is going to come out, because if it didn't, it would warm up, right? How much thermal energy comes out? I would avoid calculating Q directly. Why don't we just calculate W? Because the delta E is 0. See my point? And so this is an example of, I would not even try to go through a process of calculating Q. I would go through a process of calculating the W, knowing that the delta E is easy. And then I can get the Q there. And so that's how I'm going to find my Q. So what I'm trying to set you up for is, of course, notice it's path dependent. But notice it becomes a little puzzle. If you like little games and puzzles, you're going to love this. You're going to go, okay, how do I take this and change it to this to make it into this to get to here? If you hate those things, you're going to hate thermodynamics. You're going to say, oh my gosh. And that's been my experience over the years. Students either really love thermodynamics because they see how powerful it is and why it is so far-reaching. And it's why all of you have to take advanced thermodynamics when you graduate, or when you transfer, you know. It is extremely powerful and far-reaching. But on the other hand, it's a lot of puzzle pieces. It's a lot of, okay, I can't do this path, but and so solving a little maze, solving a little puzzle is what this is going to turn into be. And that's kind of the step. Calculating Q in this case would be extremely hard, but calculating the W is not, and the E is not. So go that direction for this one. Yeah.
So on the graph on the right, as you're pushing down, it's going to be the most difficult at the very end.
Oh yeah.
Right? But on the left, it would be the same difficulty all the way through.
Yes. Yeah. Yeah. Defining difficulty is how much pressure there is.
How much force you have to put on it.
Yeah.
We'll get that much further.
Yeah. Which is connected to how much pressure there is. So, yeah. Yeah. Why is what? Oh, good. Don't miss this. This. If you miss that, you could struggle on this problem for hours going, I can't get the Q. See, I can get the W, but without knowing the E, I can't get the Q. So then you're going to want to do the Q. But that's not the best way to do it. So why is the delta E 0 is his question. Well, back to this, delta E. What is the delta E of a gas? It's the internal temperature of those molecules bouncing around. It's the kinetic energy of those molecules bouncing around. Their kinetic energy is their temperature. So if their temperature increases, their delta E increases. If their temperature decreases, their delta E decreases. But if their temperature remains the same, then delta E doesn't change. That's the key, right there.
Well, there is no net change. There is some change because if you compress, you make a little bit of heat, but the heat gets drawn away.
Okay, yes, and all of this is what you might call equilibrium. This is, okay, I first compress it, it warms up, then the heat comes out. Okay? So, yes, it is the net change. So the net delta E is 0. Well, in the quick moment we have left, and then I guess I won't be able to show you the conduction one yet, but I guess we'll do that on Tuesday here, is the last process is what if the Q is 0? And this is the one I've been showing you. This is the one I think is the hardest one to grasp, and it's the reason I started showing it last time and continued to show it today. It's this 2-liter bottle. What happens when I open that valve real quick? It expands really quick, right? So quickly that what we could say is the Q is 0. Now, after a couple minutes, that would not be a fair statement. But if you were to take something very quickly, as somebody pointed out, what about gas that burns inside the cylinder of my car? Boom, real fast. Piston goes down. All this happens in a fraction of a second. Yeah, some of the heat is going to transfer to the walls. That's why we have to have a cooling system on our car. But as a rough first year, first approximation, I could say no change. Okay? Same thing you saw here. You saw me pump it real quick, it warmed up. Of course, once I stopped pumping it, what did you see? Yeah, then you saw it cool down. Then you saw the Q change. But anything that happens really, really quick, or there's other options too. But what I've shown you so far is what I call the adiabatic process. That if it happens real quick, there's not time for Q to change. Or, in the case of our atmosphere, the gas is so big. I mean, you're talking about air expanding or compressing that is miles, maybe hundreds of miles. And so as the air compresses and expands, you just don't have enough time, or even if it's hours, something that is hundreds of miles wide, you just won't get much change in thermal energy by then. So this process is called the adiabatic process. And what's nice about the adiabatic process here is that the Q being 0 means that the delta E equals what? The work. Because the Q is 0. And so on a PV diagram, what am I going to see? Yeah.
Is this kind of like the last case where the temperature's not taken?
Wait, okay. And so this, maybe I'll do this. I'll draw a dotted line here to represent the isotherm. You can kind of see when you compress something real quick, what's going to happen is the volume's going to go down, the pressure's going to go up, but also what happens is the temperature goes up. And so that didn't happen for our isotherm. So probably the best picture I could give you is a picture that is comparing an isotherm and an adiabatic. Why would the pressure go up a little bit more? Yeah, because the temperature went up a little bit more, right? We're not giving time for the molecules to get rid of that energy that was added to them because of the compression of the gas. And so the adiabatic and the isothermic process look a lot the same. At least on a graph. Do they have the same shape? No. What is the equation? Well, we'll stop here. And we'll leave you on a cliffhanger here for that one there. But it's going to have a more complicated shape. And it's really going to take till the next chapter. We're not even going to do it in this chapter here. But so we've got some work to build up to that one.